Good afternoon, everybody, and welcome to the webinar, Industry 4.0 Leveraging Machine Data for Business Success. My name is Caroline Stewart, and I'll be the moderator for the webinar today. I have with me Tanai Pant, who will be the presenter for today. And before I pass over to Tanai, I'm just going to go through a few housekeeping things just to make you aware. We'll take questions at the end of the presentation, but if you do have any questions, then you can ask them in the questions panel, which you should see on the screen now. We also have a couple of polls, which we will be asking you throughout the presentation, so watch out for them. And also, if you have a problem with the sound or you can't see the presentation or anything like that, please just let me know through the chat. And lastly, we will be recording this session, so we will be sending it out within the next few days, so please watch out for that too. And with that, I'd like to hand over to Tanai.
Thanks, Caroline, and hello everyone. Welcome to today's webinar on Industry 4.0, Leveraging Machine Data for Business Success. I'm very happy to see all of you here. Today, we will talk about a couple of topics, which include the Industrial Revolution, what were the different stages of industrialization, why they were meaningful, and understand what is Industry 4.0. We will then talk about sensors in factories, why it makes sense to use them there, and the kind of workflows that they enable in an industrial context. We shall also talk about what exactly time series data is and how sensors and time series data are related to each other. After that, we will take a look at the Cray DB ecosystem and learn about the characteristics of Cray DB that sets it apart from the other databases in this segment, as well as why it makes sense for you to incorporate Cray DB in your smart factory infrastructure. And finally, we will go through a case study of a smart factory which has made six-figure savings in 2018 by making a switch to Cray DB. My name is Tanai Pant, and I currently work as a developer advocate at Cray.io in Berlin. I really enjoy working with time series and sensor data. I'm a tech speaker for Mozilla and volunteer to their various projects in my spare time. I have published books on Firefox OS, building a virtual assistant on Raspberry Pi, and web-based virtual reality. I'm also an Intel software innovator in the field of IoT. And towards the end of this webinar, I will share my email and Twitter handle. So if you have any questions after the webinar or have any interesting project ideas, I would be really happy to collaborate. Please feel free to get in touch with me. So let's get started. So dating back to around 1760, the first industrial revolution was the transition to new manufacturing processes using steam and water. It witnessed the emergence of mechanization, a process that replaced agriculture with industry as the foundations of the economic structure of the society. So it was hugely beneficial in terms of manufacturing a large number of various goods and creating a better standard of living for some. The textile industry in particular was transformed by industrialization, as was transportation. Mass extraction of coal, along with the invention of the steam engine, created a new type of energy that thrust forward all the processes, thanks to the development of railroads and the acceleration of human, economic, and material exchanges. So this made machine use even more feasible, and the idea of manufacturing with machines quickly spread. Machines allowed faster and easier production, and they made all kinds of new innovations and technologies possible as well. By the beginning of 20th century, electricity became the primary source of power. It was easier to use than water and steam, and enabled businesses to concentrate power sources to individual machines. Historians sometimes refer to this as the technological revolution. So this period also saw the development of a number of management programs that made it possible to increase the efficiency and effectiveness of manufacturing facilities. Mass production of goods using assembly lines became commonplace. Lastly, just-in-time and lean manufacturing principles further refined the way in which manufacturing companies could improve their quality and output. All of these inventions were made possible by centralizing research and capital structured around an economic and industrial model based on large factories and the organizational models of production. Then, around 1970, The third industrial revolution involved the use of electronics and IT to further increase automation in production. Manufacturing and automation advanced considerably in that period, thanks to internet access, connectivity, and also renewable energy. So Industry 3.0 introduced more automated systems onto the assembly line to perform human tasks. Although automated systems were in place, they still relied on human input and intervention. Later on, the invention and manufacture of electronic devices such as transistors and integrated circuit chips made it possible to more fully automate individual machines to supplement or replace operators. This period also spawned the development of software systems to capitalize on the electronic hardware. So integrated systems such as material resource planning were superseded by enterprise resources planning tools that enabled us to plan, schedule, and track product flows throughout the factory. Now here we are, the fourth industrial revolution. So the fourth industrial revolution is the era of smart machines, storage systems, and production facilities that can autonomously exchange information, trigger actions, and control each other without human intervention. So it connects the Internet of Things with manufacturing techniques to enable systems to share information, analyze it, and use it to guide intelligent actions. It also incorporates cutting-edge technologies, including additive manufacturing, robotics, artificial intelligence, and other cognitive technologies. The development of new technology has been a primary driver to the movement to Industry 4.0. The applications for the industrial sector are already enormous, such as predictive maintenance, improved decision-making in real time, anticipating inventory based on production, and improved coordination amongst jobs. Now that we know what the four industrial revolutions were and what Industry 4.0 is, let's talk about sensors in factories. So smart factories have a large number of sensors for monitoring a large variety of things, such as temperature, pressure, or humidity. Every day, millions and billions of data points are generated by sensors in smart factories, smart cities, and the health industry. And this data needs to be ingested in real time. Since the different sensors are produced by different manufacturers, this data tends to be complex and can be in many different forms. And this data has valuable insights about the operation which can be obtained from it by performing analytics on the data in real time. Queries like aggregation and time series analysis, along with machine learning or predictive analytical models, are often applied on this data. The insights produced by these analytical operations can be used to take action to improve the efficiency and functioning of these various industries, hence causing significant cost reductions. But the differentiating factor that should be kept in mind as compared to other time series use cases is that these queries are under highly concurrent load. For example, stream processing and machine learning, and must access gigabytes to hundreds of terabytes of data. So before delving into how the various sensors and time series data work with each other and are interrelated, let's talk a bit more about time series data itself. So the million-dollar question, what is time series data? And most importantly, how does it differ from other forms of data? To answer this question, imagine a sensor. This sensor is sending streams of data over a period of time. Now, if you were to plot the data onto a graph, one of the axes would be time. And as compared to some other workloads, this data is not added as an update to the database. So if you think of a platform like WhatsApp or Telegram, each time you set a new status, it rewrites your previous one, as this change is made as an update to the database. Time series data is added as an insert, and this is the primary way of adding time series data to a time series database. Now, time series databases introduce efficiencies by treating time as a first-class citizen. Having such a rich amount of historical data allows you to delve into all the aspects of your operation, such as analyzing the past, monitoring the present, and predicting the future. Now that we have an idea of what time series data is and what it tends to look like, Let's play a game that I like to call time series or not. Callan, would you be kind enough to send through the poll? So, is the data that is denoted by this graph time series or not? So you can send your answers via the poll. I will wait for a few seconds from this. All right. Can we turn this off, Callan?
Sure.
Okay.
There you go.
So, as all of you correctly guessed, yes, this is an example of time series data, as we are measuring metrics such as temperature and pressure against time. Time series or not? Let's take a quick look at this and let's launch the poll. Okay, we are going to wait for a few seconds here. And let's switch off the poll now. Awesome. So correct again. So no, this is not an example of time series data, as we are measuring the production of good and bad bottles against the different production lines. Last one, time series or not. Take a good look at the graph, and here we have the poll. I'm gonna wait another few seconds. Okay, I guess we can turn this off now. And awesome, again, all of you are correct. So here again, we have an example of time series data, as we are measuring the downtime hours of the New York and Florida factories against months, which is essentially time. Now, if you take an abstract look at the use cases of time series and the kind of data generated, you can categorize them roughly into two types. So first of all, we have IT and system monitoring. So this can be termed as the traditional use case of time series databases. So this can be characterized through tens of hundreds of metrics or sensors, real-time write functionality, rarity of complex queries, and data volumes that fall in gigabytes. So if you think about the different time series databases, InfluxDB is an excellent example as a database for this category. And then we have industrial sensor data. So this is an emerging sector that I feel has not been talked about enough. So this is characterized through hundreds of thousands of metrics or sensors, real-time queries that are under highly concurrent load and must access gigabytes to hundreds of terabytes of data. Cray DB is an especially good fit for this category. And then there are other characteristics that separate the two use cases, like the projects that fall under the first category tend to be internal IT services, and the data in the database or monitoring are often not that mission critical. As opposed to that, the projects that fall in the latter category are often mission critical, transformative, and enable real-time data-driven decision systems. Industries all around the world have been working with a number of different solutions to transform the way that their manufacturing processes work. These systems aim to control and provide real-time feedback by recording data from different sensors, motors, and valves. And all this data that is gathered contains multiple values and parameters, along with a timestamp, which we learned earlier makes it time series data. And this complex time series data coming in at high speeds also needs to be queried in real time. And hence, this data is sent to a time series database like Cray DB and monitored visually via a dashboard like Grafana, Power BI, or Apache Supersets. And if you take a look at the last decade, you can say that it's a machine data world. And machine data means explosive growth. In 2018, we saw a boom in the number of IoT devices and their use cases. There was an increase in the use of IoT and sensors in different contexts, such as smart factories and smart cities. The total number of IoT devices is moving towards 20 billion by the year 2020, and every second, another 127 devices are being connected to the internet. Just as an example, think of a Boeing 787, which generates half a terabyte of data during a single flight. And if we talk about the plastic manufacturing industry, there's a wide array of data being produced per bottle, and there's data per production line with as many as 10 production lines per plant. And this data is being generated by around 950 different sensor types. And that's just one factory. And this particular company has 180 factories in 45 different countries. That means data on billions of bottles. There's a good chance that the bottles that you use in your refrigerator have been running its data through the Crate platform during their production cycle. But we shall talk more about this company and the data generated by it in a while in our case study. So at Crate.io, we have been working on developing technical architecture in the IoT and time series field over the past 5 years. We have a co-selling agreement with Microsoft, and our client portfolio includes companies like McAfee, Nokia, Rauch, Alpla, and many more. Earlier this year, Crate.io was also named a Cool Vendor in the Gartner 2019 Cool Vendors in Manufacturing Operations report. To learn more about the Cray DB ecosystem, let's start off by going into the heart of the honeycomb to the core technology and talk about Cray DB and what makes it stand apart from the various other databases in this segment. So Cray DB is a new kind of distributed SQL database that is best suited for handling industrial time series data due to its ease of use and ability to work with many different terabytes of time series data with thousands of different sensor data structures. So CrazyB is quite simple to install. You can spawn an instance of CrazyB with a single line on your terminal or on Docker. CrazyB uniquely combines SQL with NoSQL benefits. So it operates on a shared nothing architecture. That means the various nodes in a cluster coordinate seamlessly with each other, and the execution of write and query operations are distributed equally throughout the nodes of a cluster. It is ANSI SQL compatible, including joins and Postgres via protocol, which make integration with tools such as Grafana really easy. And it also prevents lock-in. CrazyB supports distributed SQL with full-text search, JSON, time series data, geospatial data, and even blob tables. This architecture is quite well suited to containerization, meaning a cluster running on Kubernetes can be scaled up or down as easily as running a kubectl scale command. Because of this, scale-up operations can take minutes instead of weeks with CrazyB. And operations such as sharding, replication, and rebalancing of data as the cluster size changes are automated. Until recently, workloads like these often required a NoSQL solution like Cassandra, Elasticsearch, or InfluxDB, often in combination with a traditional relational database. CrayDB makes it possible to handle them in a single system without sacrificing the familiarity and power of SQL. This fire hose of complex data needs to be handled in real time in order to take real-time actions on the factory floor. Let's now talk about the next layer of the honeycomb built on the core CrayDB technology, CrayDB Cloud, also known as CrayDB on Azure. So CrayDB Cloud is a scalable SQL cloud service hosted on Azure and operated 24/7 by the experts at Crate.io. It is ideal for industrial time series data processing and other IoT and machine data specific analytic workloads. So some of its salient features are that it has real-time query performance for partitioning, parallel processing, and in-memory columnar indexes, which enables real-time complex analytics and AI, not just simple time series aggregates. It also has Azure IoT integration via built-in interfaces to Azure IoT Hub, MQTT, Postgres via protocol, JDBC, REST, and a native .NET Core driver. And this brings us to the next layer of the honeycomb. So this is the Crate IoT data platform built on the top of CrazyB Cloud. The Crate IoT data platform makes it easy to build smart systems that collect streams of data from connected devices and sensors, enrich the data, analyze it, and then initiate action in the moment. It enables you to monitor, predict, or control the behavior of things in real time and make course corrections to improve business efficiency, profitability, and security every single minute instead of every month. So CrazyB excels at handling the velocity, volume, and diversity of huge industrial time series workloads. For example, industrial sensors often increase the frequency of their measurements when values exceed configured thresholds. With multiple sensors, cascading failures can result in huge data ingestion spikes. So CrayDB is able to handle these spikes without sacrificing query performance, meaning that your reporting and analysis tools won't just stop working just when you need them the most. And now you must be wondering, there are already so many widely used time series databases or even other traditional databases. Why is CrayDB better than them for Industry 4.0? Well, let's take a look at how CrayDB compares against some traditional databases. A while back, we put together a benchmark that compares CrayDB versus PostgreSQL, and we compared their query performances. The results of this benchmark showed that CrayDB performs significantly better than PostgreSQL with selects, aggregations, and grouping. So this was a test which simulates an application that collects sensor readings from separate customer sites and stores them in a multi-tenant database. So this is a really common case, a SaaS application that enables customers to monitor sensor data via real-time dashboards. Now this dataset contains around 314 million records and simulates sensor readings gathered over a period of 1 year. So each record of the sensor reading contains information about the sensor, and it has readings such as UUID, which is a universally unique identifier for the sensor reading, a timestamp of the sensor reading, the ID of the customer tenant from which the sensor is reporting, ID of the sensor, type of sensor, and two sensor readings in the form of an integer, two in the form of a floating type number, and one of Boolean data type. And finally, we had a generated column that contains the week of the timestamp for indexing or partitioning. So with this data, we benchmark a scenario that is very common when dealing with large amounts of numerical sensor data, aggregations. So aggregations like averaging and totaling are everyday queries that are quite useful in real-time analysis and sensor data. So this benchmark simulated multiple users querying the 314 million row database concurrently. So three different SQL queries were used, and the parameters in the query were randomly generated to ensure the queries produce different responses as they would in real life. So with the exception of the full text query for CrayDB, the SQL syntax was same for both CrayDB and PostgreSQL. So we used JMeter, and a JMeter test harness simulated 30 concurrent users, each connecting to the database and executing the three test queries in random sequence, and of course with random query parameters. And each database executed over 4,000 queries during their respective benchmark runs. So the results that you can show, that you can see, these show the average duration in milliseconds for each query to process 314 million rows. So CrayDB beats PostgreSQL quite substantially when dealing with selects, aggregates, and grouping. So this is because of CrayDB's ability to distribute the workload across an elastic cluster of servers, and it has more CPU cores working in parallel for it. And this is a unique feature of a distributed system, and it allows you to scale processing performance horizontally with the addition or removal of nodes. So most SQL databases are not distributed, and so they require you to scale them vertically if you want to increase processing performance. Coming to NoSQL databases like MongoDB and Apache Cassandra have pushed database technology beyond the schema, scalability, and even performance limitations of traditional relational databases. But proprietary data access interfaces make them somewhat harder to learn. And it also makes it harder to use. It has a much more steeper learning curve and also integrate than SQL databases. And it can often cause vendor lock-in. So the newest wave of databases, including Cray DB, are distributed SQL databases built on the top of NoSQL foundations like storage, indexing, networking. And these combine the familiarity of SQL access with the versatility and scalability of NoSQL. So let's take a look at how they compare against CrazyB. So let's first talk about cluster type and scaling. Both CrazyB and Cassandra have a shared nothing architecture as opposed to MongoDB, which has a master-slave architecture. CrayDB supports ANSI SQL via JDBC, ODBC, REST, and Postgres via protocol, as opposed to MongoDB supporting MongoDB query language and Cassandra supporting its own Cassandra query language. So by supporting ANSI SQL, CrayDB makes data management much simpler for mainstream SQL developers, who, by the way, still outnumber NoSQL developers by a 45-to-1 ratio according to LinkedIn. While MongoDB supports dynamic schema, Cassandra only supports static schema. So CrayDB also supports dynamic schema, SQL DDL plus JSON objects, and even arrays of objects. Cassandra supports columnar indexing, unlike MongoDB, and CrayDB supports memory-resident columnar caching. So CrayDB has columnar caches for real-time in-memory SQL performance. The issue with real-time databases is that they usually require all the data to fit in the main memory, but that kind of limits how much data you can manage. So our solution for real-time performance without data volume limitations was to implement memory-resident columnar field caches on each node. These caches tell the query engine whether there are records on that node that meet the query criteria and where those records are located. And this all is performed at in-memory speed. So distributed query processing also contributes to fast performance and a query planner that makes very smart decisions about which nodes are best suited to perform different aggregations and joins. And speaking of aggregations and joins, CrayDB supports aggregation queries and full joins, whereas neither Cassandra nor MongoDB support this. Finally, we have geospatial queries and full text search. Both Cassandra and MongoDB have limited support for full text search and no support for geospatial queries. So CrayDB has Lucene Power support for both of these functionalities. And to summarize all of this, Cassandra and CrayDB both feature columnar indexing, data compression, and eventual consistency, which make them good fits for analytic applications that deliver fast query performance against streams of data or very large data volumes. But as you might have heard, Cassandra is famously hard to change and optimize as application requirements evolve, whereas CrayDB is not. And support for data aggregation, text search, joins make CrayDB an easier fit for time series and many other types of use cases. Now, MongoDB tends to be used more for user interactive transactional applications, and CrayDB is better suited for query and insert intensive analytical applications. CrayDB also scales much more easily and reliably due to its shared nothing architecture versus the Mongo cluster with its specialized writable nodes and read-only nodes, as it has a master-slave architecture. And if you need full schema flexibility, query versatility, and performance, CrayDB is the better fit. Now, time series application developers often compare CrayDB against single-purpose time series data stores like InfluxDB. Now, CrayDB and InfluxDB have many important functional similarities. That's true. So some of these similarities are both excel at ingesting streams of time series data, both can partition, query, and aggregate timestamp index data in real time, both can handle structured and both unstructured data, both support data compression, and most importantly, both are open source softwares. But unlike InfluxDB, CrayDB includes ANSI SQL standard access interface. In CrayDB, there is no limit to the number of columns that you can add in a table. And you can add columns and indexes on the fly as well without having to dump and reload the data. In InfluxDB, the number of columns per series is limited to 200, and the columns by which a series can be indexed and queries are fixed at the table creation time. So if you want to add a new tag column, you must first redefine and reload the series with the new tag column. And to build richer time series applications, CrayDB supports geospatial queries, full text search, table joins, subqueries, and even user-defined functions. So they are quite useful user-defined functions for functions related to artificial intelligence or anomaly detection. So these features basically save you time and work. Now for performance benchmarking, we use the same data set that I mentioned we used for PostgreSQL. So we had 314 million sensor readings which were stored in Cray DB and InfluxDB, each running a similar cluster, and the hardware was exactly similar. So we had clusters with 24 CPU cores and 48 gigabytes of RAM, and queries that access data from a single partition, so queries 1 and 3 in the graph within the same week, worked fast in both databases, but faster in InfluxDB. But a query that spanned multiple partitions, which is the query 2, ran 4 times faster in CrazyB. Now, if you take those same queries and run them under load, simulating multiple users querying the database at the same time, the performance of InfluxDB begins to degrade. And the average query time gradually increases as users are added to the workload in InfluxDB. So it finally begins hitting a wall at the 40 concurrent user mark. So reducing the number of concurrent connections to 20 for InfluxDB and CrazyDB, a query throughput comparison shows CrazyDB processing about 10 times more queries per second than InfluxDB. So to conclude CrazyDB versus InfluxDB, CrazyDB provided better query performance when answering queries for bigger user bases or when querying bigger data volumes, which is across multiple time partitions. And if you compare time series databases for your project, take into consideration the functional and performance advantages of CrazyDB. Now, let's take a quick look before going into the case study at the licensing options for CrazyDB. First of all, we have CrazyDB, which is the core database offering and can be deployed on-premise or on any cloud. It is licensed on the basis of a software subscription and can be deployed on a customer's existing Azure subscription. For example, bring your own license to your Azure subscription. And furthermore, it is free if the deployment of CrazyDB is limited to just 3 instances. And then we have CrazyDB Cloud. So CrazyDB Cloud is a managed service we talked about offering directly from Crate.io, where the database is deployed and managed on the Crate Azure subscription on the behalf of a customer. So this is a bundled SaaS offering, often referred to as database as a service. Now, as promised, I would like to share with all of you a story of one of our customers named Alpla. So most of the people in the world use their product at least once a week, be it Coca-Cola, Head & Shoulders, or Dove. Alpla is quite well known in the consumer packaged good markets for its innovative packaging systems, bottles, closures, and injection molded parts. So in 2017 alone, Alpla produced over 100 billion consumer goods packaged. And with over 100,000 tons of recycled plastic, it is also one of the leading packaging companies when it comes to minimizing plastic waste and plastic reuse, also known as the closed-loop plastic economy. And we have been working with them over the past 3 years. So this is where real-time information from the production floor has the potential to add value to 180 manufacturing sites in 45 different countries. They have sensors for temperature, pressure, blending ratios, and other settings that need to be really precise on every machine. And when these settings are right, high-quality products are the result. And when these settings are off, quality suffers, and also the production costs increase. So imagine a factory floor with 4 production lines. And each of these lines, let's say, have 4 pieces of machinery each. So in the factory, they usually have some sort of visual indicator which shows if everything is working smoothly or not. So in order to discover these issues, multiple people were required to be continuously moving around the factory floor, checking up on every single machine. Now, one of the typical scenarios that can happen is that an employee is currently working on fixing an issue on the production line 1. Once they finish that, they have to go through all the other lines to check up on the machines and their visual indicator. And that is when they spot that there seems to be an issue on production line 3, machine 4. So the person after their current issue goes to production line 3, machine 4. And upon taking a look at what's up, they realize that some parameters needs to be readjusted on the first machine in this production line. And then the person moves again to the first machine to fix the underlying issue. Now, in factories, the production lines are laid out over the whole factory, and distances between machines can be considerable, meaning that this was a really slow and labor-intensive process. Additionally, the latency that was introduced by having to walk around the factory meant that many products were often affected by a defect even before the error was spotted by an operator. So this resulted in the loss of valuable machine time and the loss of raw material, as defective material gets produced till the problems are solved. Now, Alpla's market entry in North America in 2001 was followed by years of tremendous growth. In 2015, it was already operating 14 manufacturing plants with more than 1,000 employees in the USA. And with this growth came the challenge of hiring and training enough personnel to run the complex manufacturing processes. And because modern manufacturing machines each have a different sort of complex user interface, every plant required specially trained experts for every single machine on every single shift. Now, as a result of this rapid growth, the database performance degraded, and the response time for queries got longer and longer, and any analytics work on the data was taking more and more time. So real-time actionable guidance on the production floor was no longer possible. So Crate.io built their proof of concept on the top of Cray DB cloud and enabled them to drive technological transformations. So the first step was to send data to Cray DB alongside the existing SQL database. So performance of the system improved immediately. Reports and analytics could be generated in seconds instead of minutes. And the system became capable of giving real-time actionable guidance for workers on the production floor. So this allows Alpla to establish a closed loop of continuous production state monitoring and process improvement based on what is read from these machines. So when the Crate IoT data platform detects or predicts an unusual change in the state of data, it alerts an expert factory operator in mission control. Now the mission control for Alpla is based in Atlanta and looks like this with dashboards for different factories from which we get the raw data. And this is an actual picture from the Atlanta mission control. Now the operator alerts somebody at the machine in the factory via a mobile notification system, suggesting either an adjustment or a repair. Now, since the employees on the production floor has real-time actionable guidance, while they are fixing the first issue, they would get a notification that something is up on the production line 3, machine 4, and that person needs to make adjustments to the first machine of that line to resolve that issue. And this way, once the person is finished with their current machine, they can head over directly to the appropriate machine to resolve the next issue. And they no longer need to go through the whole factory, checking upon every single machine, making sure that it's running properly. And after this issue is resolved, the factory operator logs a note explaining how the issue was resolved. Now, notes are shared via online manuals across all the factories to improve knowledge sharing of best practices. And that is how we close the loop by using this data to take real-time actions on the factory floor. So every plant in Alpla using Cray DB saw improvements in net equipment efficiency, with some having efficiencies above 90%. So this NEE, or the net equipment efficiency, was one of the parameters they used to determine how the factory is performing. And every plant also saw a reduction in manual process adjustments by as much as 50%. So reducing the number of manual adjustments stabilizes the process and significantly improves production efficiency. So the result was a 6-figure saving in 2018. Currently, there are about 2.5 million queries per day, and work hasn't even finished yet. It is estimated to increase about 18 times by the end of 2020. And with this, I would like to conclude today's session on Industry 4.0, leveraging machine data for business success. We talked about the 4 industrial revolutions, sensors in factories, how sensors and time series data are related, the Cray DB ecosystem, along with some comparisons and benchmarks, and we finally did a case study on how Alpla made technological transformations with Cray DB, along with a sweet 6-figure savings in 2018. So we are currently in this booming age of data. Why not put it to work to make our lives easier, safer, and better? I look forward to seeing what you do with this. Thank you very much. I guess we can take questions now, Carolyn.
Sure. I can see a few coming in here. So Do you want me to just jump in and read them out to you? Is that okay?
Sure, that would be great. Thank you.
Cool. Okay, so the first question is, do companies other than manufacturers use Cray DB in production? And then there's a second part of this. What kind of use cases do they have?
That's a very good question because, like we have in this talk or webinar, we have been exclusively talking about the industrial use cases. But in terms of use cases other than IoT and sensor data, CrazyB is quite relevant for use cases having geospatial analytics, application analytics, and even running real-time analytics on streams of network, IT events, and log data, like that kind of stuff. And just to give you an example, McAfee is one of our customers. And after implementing Cray DB, they reduced their hardware and costs by as much as 75%. I hope that answers the question.
Great, thank you. Okay, there's another one here. Deploying new technologies to effect transformation usually begins with a transformation of existing beliefs and mindsets. How do you work with customers to help them understand how Cray.io can modernize their existing process?
Okay, so if you think about it, Industry 4.0 has been cited as the next revolution in the industrial sector, with smart machines and intelligent services delivering productivity benefits to manufacturers. Now, a lot of companies have struggled to capture and analyze the data being produced by these smart machines in their factories, right? So database infrastructure has really limited companies' ability to scale their facilities, preventing this kind of real-time data-driven decision-making that we talked about and plant-wide insights. So I feel like there are really three main beliefs in this context of transformation that we try to transfer in our conversations with customers. So I split that into three parts. So the first thing is you need the ability to capture, process, and analyze massive quantities of machine data in real time. And if you can't do that, you'll always be one step behind your competitors. Then second is, in order to make your decisions instantly and in real time, you need an instantly scalable solution capable of handling thousands of sensors across multiple production lines. So the infrastructure complexity and the amount of sensors in production facilities absolutely require a solid foundation. So the time series database that you use must be like the air that you breathe. That's what our CTO says. And it's the very basic thing that gives you everything that you need in order to survive. And the third important aspect is you'll always need a global connectivity and oversight to compare worldwide facilities. And this is not only necessary for production processes and involvement, but it's also very important for a cybersecurity point of view. So you absolutely need a very secure IT infrastructure to protect these critical facilities. So I hope that answered the question.
It did, thank you. Would you like to, have we got time for one more? I know we're just at the
sure.
end. Okay. How many nodes does Alpla use and how many data points do they have?
Okay, so Alpla has a five node cluster. And the number of records that they have are constantly changing. But let me take a quick look. I mean, the first time I talked about Alpla, they had around, I don't know, 2.6 billion records. Now they have 3 billion records at this point. So they have a five node cluster, and currently they have around 3 billion records in that cluster.
Wow. So I can see another couple of questions coming in, but we will have to get back to those people by email because I think we've reached the end of the time.
Sure, sounds good.
So with that, I'd like to thank you all for joining us today. We have recorded this session. We'll be sending out a link to the recording, and also if we haven't answered your questions, we will get back to you. Thank you and enjoy the rest of your day.
Thank you very much, everyone.